Good afternoon, everyone. This is Kimia Tasnio. I am going to present my paper summary with you. So I will going to cover 4 papers in the verification of VLSI domain. So the first paper is the functional verification of DSP based on onboard VLSI designs. This paper is about making it much easier to verify complex DSP blocks that sit on board in space or embedded systems. Think of big FFT cores or single cosine lookup tables. They are mathematically heavy, highly optimized, and often implemented in fixed point. Writing a full bit accurate checker in System Verilog for each of those is painful, slow, and very easy to get wrong. So the author's idea is instead of reinventing all the math in the test bench, use MATLAB, the tool DSP designers already trust, as the golden reference. So the verification environment is built in System Verilog or UVM like usual. You have constraint random stimulus driving the duty, monitors collecting outputs, and a scoreboard deciding pass or fail, as we do in the UVM. The twist is inside the scoreboard. What is that? That is when a transaction comes in, the scoreboard calls out through a TPI-C wrapper into MATLAB, passes the same inputs that DOT saw, and asks MATLAB to compute the correct results using its built-in FFT or sine cosine functions. Including fixed point conversations, the MATLAB results comes back through the C layer, gets compared to the DOT output, and any mismatches are flagged. So very smart and simple, right? Finally, they demonstrate this on 2 real space-borne IPs for the 8192 point FFT. Overlaying the DOT spectrum with MATLABs reveals subtle precision and register length effects that would be hard to spot otherwise. For the sine cos ABUT, they can literally sweep all 2 to the power 16 possible input angles and verify that every 10-bit fixed point output matches MATLAB. The takeaway you can emphasize is that this flow reuses trusted MATLAB models, reduces the effort to build checkers, and gives much better visibility into DSP behavior, while still fitting cleanly into a standard UVM verification environment. So the next paper is the system verification methodology for advanced TLM verification. So this paper is about bringing UVM style verification into system CTLM, or a little bit different, but has kind of similarity of the previous paper. System C is great for early transaction level models, but it doesn't natively support strong constraint random and coverage driven verification. Existing libraries like OVM SC and SCV only cover parts of that, so people end up with ad hoc test benches that aren't as rigorous as we do at RTL with UVM. So in this paper, the authors propose SVM, the System Verification Methodology, a UVM-like library for System C. It gives you familiar components like test, agents, drivers, monitors, sequencers, sequences, and plugs in a System C coverage library, plus Crave for powerful constraint random generation. They demonstrate it on a virtual self-balancing EV platform. An SVM test creates an agent around the TLM duty. The sequencer generates constraint random steering and speed commands, and driver sends TLM transaction, and the monitor and subscriber collect coverage on command types and sequence patterns. The key point is the SVM and Crave can handle complex command sequences constraints that SCV struggles with, enabling true coverage-driven constraint random verification directly at the TLM level, much earlier in the flow. So the next paper is QMC, a formal model checking verification framework for superconducting logic. It is a recent paper from 2021. So this paper brings formal verification to superconducting SFQ logic. So this behaves very differently from CMOS. Signals are pulses, gates are inherently clocked. The designs must obey strict fan-out and path balancing rules. Those quirks break many assumptions in standard verification flows, and existing semi-formal tools like VerySFQ don't scale well. The authors introduced QMC, a model checking framework tailored to SFQ. Starting from a BLIF netlist, QMC runs structural checks for fan-out and path balancing, then automatically generates SFQ style Verilog, a system Verilog wrapper with formal assertions and configuration files for open source engines like USYS, EBMC. The model checkers then either prove these functional and timing properties or produce counterexample waveforms when they fail. On benchmarks such as Cook-Stone adders, multipliers, and dividers, QMC finds both functional and structural bugs and can be up to about 20 times faster than VerySFQ. That's impressive. The main takeaway, QMC turns SFQ verification into an automated open source formal flow instead of relying on slow ad hoc semi-formal methods. So the last paper I'm going to present is paper 4 on application of error detection and correction techniques to self-checking VLSI systems. So this paper is a survey-style overview of how error detection and correction techniques are used to build self-checking VLSI systems, especially as technology scale down and soft errors become more frequent. The basic problem is that smaller feature sizes and lower voltages make circuits much more vulnerable to transient faults, which is unacceptable in safety critical domains like aerospace, automotive, and medical. Designers therefore need mechanisms that can detect and sometimes correct errors during normal operation without relying on external testing. The authors walk through the main classes of fault tolerance strategies, fault avoidance versus fault tolerance, and then focus on concurrent error detection using coding technique. They compare common codes such as parity, Hamming, Berger in terms of fault coverage and area overhead. The key takeaway is that residue codes, and in particular modulo 3 residue coding, often gives the best trade-off for data path circuits. You compute a residue on the inputs, compute a residue on the outputs, and compare them. Any mismatch flags an error. The survey reports that traditional codes like parity or Hamming can add around 47 to 54% redundant area, whereas residue codes can get similar or better detection with about 40% overhead. And a real RISC-I CPU example shows only 23.6% total area increase for residue-based checking. Overall, you can get roughly 99.8% error detection with significantly less area than full duplication, making residue codes a very attractive built-in block for self-checking VLSI. Finally, if we look into the trends of this 4 paper, so first of all, across all these 4 papers, you can see a common story. Verification and reliability are getting more automated, more rigorous, and more domain specific. The DSP paper shows how we can plug MATLAB directly into a UVM testbench and reuse trusted DSP models as golden reference instead of hand coding complex math in System Verilog. The SVM paper does something similar at a high level of abstraction. It brings UVM style components, constant random generation, and functional coverage into pure system CTLM. So we can do coverage driven verification much earlier in the design flow. The QMC work moves from simulation into full formal. It tailors model checking to superconducting SFQ logic with the right structural checks and temporal properties, and then leverages open source engines like USYS, SMT-BMC, and EBMC to either prove these properties or give counterexamples. Finally, the self-checking VLSI paper looks at the infield side of the problem. Instead of just finding bugs before tape-out, it surveys on-chip error detection schemes and highlights residue codes as a way to get near duplication level fault coverage with much less area. So the key similarities are all four are trying to close gap in existing flows. They all rely on same form of reference behavior or properties MATLAB function. TLM platform behavior, SFQ, assertion, residue invariants, and they all aim to boost confidence without exploding cost. The main difference, I would say, are in technique and timing, simulation plus coverage versus formal model checking versus hardware error detection, and pre-silicon design verification versus post-silicon runtime fault detection. Together, they span a continuum from better test bench to better formal proofs to better self-checking hardware. Thank you so much for joining. Have a great day. Bye.